Are you a data engineer, data scientist, or stakeholder in big data and AI? Do you want to process your big data lightning fast and efficient for your analytics use cases? Then you should know about Apache Spark, a state-of-the-art framework for data processing and more. It's simple, fast, scalable, and reliable. And on top, cloud providers like Azure and AWS support it, fully set up. And with this, a warm welcome to another session, Data with Nikk the Greek. This is going to be the first part of the series, Spark Basics Simply Explained, and also my first PowerPoint. So a non-coding session. And today we really want to show the basics, how Spark can really boost your big data processing. Concretely, we're going to talk onto two topics. What are the core features of Apache Spark? And on a very simple basics, basis, we're gonna look how it works, lightning fast, of course. And before we are gonna start with our topics, I just want to mention, if you want to see more of those videos, as always, please subscribe below. You can either click on my channel or you should see a red button on the right side of the screen. And also what I want to mention, I heard that sometimes the quality seemed to be not perfect. That's unfortunately something from YouTube side. You can just set it up on the settings button below where you can set up the quality a little bit higher. All right, let's talk about the key features of Apache Spark. So when you're visiting the website, you're gonna see this promotional screen that it's simple, fast, scalable, and unified. And that's something we're gonna see in the next slides. We're gonna unified already, you see it in the key features on the right side. So the most important thing is you can do batch and streaming data processing. So really unified into one framework, which is pretty amazing. And you can use multiple languages. Python, SQL, Scala, I would say, are the more famous one, but also Java and R can be used. In my videos later on the coder sessions, you're gonna see that PySpark, meaning Python, is my preferred language. Also, together with the so-called Hive Metastore, you can run SQL queries. So you have the SQL database like feeling on top of Apache Spark. And also it's capable of exploring and processing petabytes of data. So you're gonna see also when we jump into the architecture a little bit how it actually is capable to do this scaling of petabyte data for data science, but of course also for data engineering. And I think that's also a really important point. Usually people know PySpark from data engineering side, but also data scientists can do machine learning in a distributed, more performant way. Usually like people use for classic machine learning, scikit-learn, for instance, but there are also some issues or some efficiencies which you don't have when you do it with scikit-learn, but you're gonna have when doing it with Apache Spark. Of course, the machine learning library is a little bit more limited than the scikit-learn library. An important point which I also mentioned, and that's really only a very small pick of the providers available, is that there are a lot of providers available already which have a set up distribution of Spark ready. So you just ramp up a cluster, you can already start coding and create your notebooks in the ETL pipelines. And I guess one of the more famous ones is definitely Databricks, which is available on all three bigger cloud providers like Azure, AWS, and Google. And well, basically the creators behind Databricks are also the creators of tools like Spark, Delta, and MLflow. A quite recent GA was also Microsoft Fabric, which is from Microsoft, indirectly also connected to Azure. And as I'm working with Azure, I know there are also some more tools like Synapse, and I saw even Azure Data Factory can use Spark, but I personally wouldn't use Synapse anymore, as Microsoft Fabric is basically the tool to go for Spark if you want to use a direct Microsoft tool. Otherwise, I'm not an Amazon Google expert, but Amazon EMR and Cloud Data Proc if I pronounce it correctly, other tools where you could also go on AWS and Google otherwise. Looking a little bit deeper when you are looking on the PySpark API. So which different modules do we have actually in PySpark? And we're going to go through them step by step. So the most important is the Spark core and so-called resilient distributed datasets, RDDs in short. So we have the underlying execution engine, and those resilient datasets are basically the lower level how Spark is doing the in-memory computing capabilities. And what's also important is that it's fault tolerant. So if a piece of data didn't work out to be executed on your machine, it has a logic to just recompute the piece of data which couldn't be recomputed, and this speeds things a lot of up because you have the fault tolerance, but you don't need to recompute your whole data set if you're talking about petabytes. If one piece of your data processing in your distribution didn't work successfully. And on top of those RDDs, all other components like data frames are built on top with multiple optimizations, of course. And the most important, most famous one is definitely the Spark SQL. Of course, SQL doesn't mean that you have to use SQL. It's rather the point that you now have structured or semi-structured data using data frames to work with. So like in SQL warehouse, you can also use this Hive Metastore capabilities. You can run SQL queries on top for your analytics loads, like for instance, Power BI, but of course also all your machine learning loads. And what's important is there's something called lazy evaluation, which we're going to have a look later on as well. So compared to the core and the RTDs, Spark introduced a lot of auto optimizations using a so-called catalyst optimizer. And that's exactly the part which makes Spark so efficient, the memory processing and the way as it's doing the optimizations in the background. Then for all Pandas fans who already know about data frames, you might realize when you start with PySpark, the coding is a little bit different. As a reaction, PySpark or Spark created like an API for Pandas on top. So basically you're coding in Pandas, a lot of functions, and especially the most important ones are already available. And in the background, it creates Spark queries for you. So the touch and feels like Pandas, you can easily start up just with very small code changes, and then can get started easily with Spark. Then of course we have also streaming, as mentioned in the key feature slide before. That's another API which Spark offers, and then we have the machine library. And as mentioned, it's built on Spark. It has the benefits of having distributed in-memory machine learning as well, but it's a bit more limited than scikit-learn. So you're gonna find on scikit-learn significantly more models and functions that you find in the MLlib, but may or once are available. And I'm gonna deep dive in one of my next videos into it as well. And last but not least, not supported by Python, unfortunately, but supported by Scala, is only that you can do graph processing on Spark in a distributed way. So it's called the library is called GraphX, but as far as I know, it's only supported by Scala right now. So now I already mentioned it, let's talk about why Spark is lightning fast, as it's often also promoted. So, and in short, it's what we already saw in the previous slide. It's the way it distributes data. You're gonna see it also once we jump in a bit into the architecture, and the way it's optimizing with the catalyst optimizer, which we saw. And that's exactly the difference, like Hadoop, which is also quite famous. Spark is doing in-memory processing, so that means you need quite a lot of memory in total to do your processing of the big data. On the other side, Hadoop is doing things um, on storage, pretty simply said. And there was also a benchmark where now, I think 2014 it was, the link is below. You're gonna get also the slides after this video, where there was a 100 terabyte sorting benchmark, and Spark performed 3 times faster than Hadoop. But not even that, they needed 10 less resource. I think Hadoop needed around 2000 virtual machines, and Spark needed only, divided by 10, around 200 to perform that. Generally, you can say Spark can be up to 100 times faster than Hadoop if we manage to process the data all in memory. And so we talk about simplicity in the beginning. Just one thing to mention, what's really important about Spark is to understand the architecture, because to efficiently process the data, you have at some points doing some tweaks. For instance, how you distribute your data. And let's start straight away into example for that to show. So when you think about normal Python, what's happening is you load the data. So a big data set, here we have 12 rows. Let's imagine we have million of rows and do a filtering. So the first step gonna be we load everything into memory. Then we do the filtering, and then we, for instance, do a count. So in this case, we filtered everything below 10, then we have 9 rows left, and the count returns us 9. So, and if you're doing it with a big data set, as mentioned with Python, you might receive the error of out of memory, and so will not be even able to do the count. And that's where a Spark is coming into the game. So very simply, what Spark is doing, it's cutting your data in small pieces. And those small pieces in Spark are called partitions. So those are not Hive partitions on the storage. It's a partition in memory. So I usually call it Spark partition. And then on each of these partition individually, we perform the transformation, which is here a filter. So the first 3 partitions in this case gonna still have data after the filtering, so they're gonna appear in the second step. All the other ones, I just summarized here. Of course, we will not have nearly a million or endless data into one partition. Those just gonna disappear after the filtering. And then in this distributed way, we are coming to our count 9. So we split it in small partitions, which are executing so-called small tasks later on. And the size of the partitions basically defines your scalability. So if you cut your data into 4 partitions, you can of course do only 4 executions in parallel. And it depends, of course, on how much memory you have available. So if you have a very big data set, you of course want to cut it in smaller pieces, because otherwise you're gonna have the same out of memory issues. If you have a smaller data set, or if you have a lot of machines where you can run it, you of course also want to increase the number of cutting the data into Spark partitions, because otherwise you cannot parallelize it. And that's basically the logic which we're gonna go through. If you have less data, you can of course use less machines and less partitions. And that's what we're gonna see now in a second by just jumping into the architecture. So basically, the major architecture in Spark is the following. You have a driver. So this driver is basically, let's say, like a small manager. It basically says what should be done where. And then you have so-called executors. This is generally a virtual concept, but Databricks, for instance, applied it to a physical concept. So driver and each executor are in Databricks, for instance, a virtual machine with multiple cores. So in this case, we have 2 cores each. And we have here as an example for Spark partitions. And what happens is when we're doing a a filtering, for instance, or any task, each of those cores transforms one of those partitions. So this is called a task. So if you have 20 partitions, we're gonna have 20 tasks, and each core, roughly said, gonna be executing 5 of those partitions, perform the filtering, and then do the counting. In the next video, we're gonna go a little bit deeper into how this process is working. So now we can say we have a lot of data. We gonna increase our executed, say we're gonna have 4 cores. We can also say, okay, we need more virtual machines with the same number of cores, and we're not increasing it. And of course, this is basically the whole topic about scaling. You have your data, you cut it in 2000 pieces, let's say, and of course, as more cores, and really the cores are the limiting number here, not the number of executors, define how much you can parallelize. So if you have 2000 partitions and 6 cores, you're gonna be slower than having 8 cores in some very simplified set. There are of course other topics like EO, etc., which have to be considered when making this statement. So, and of course, if you want or have a very simple data set, you might also just want to create a single node cluster where the cores of on your driver virtual machine basically are used to do the processing. In this case, we have 2 cores. Let's say we have 4 data sets. We're gonna do 2 execution rounds to do the processing. So you learned about partitions and tasks. And we also talked about the way Spark is optimizing. And one very important concept is lazy evaluation. So I just created here a simplified code similar to the example we had before with the filtering. So we read a file, we filter it based on the column which is called the ID, and then we just want to count the data. So, and what happens is Python loads all data into memory, then we do the filtering, then we are counting. And this might be fast for a small data set, but for bigger data sets, we're gonna have, or potentially the issues which we all mentioned before, out of memory, but also the performance might not be always the best because we don't have any parallelization in Python. So, and the important thing is the data loaded already after the first line. That's the most important thing. So we load all the data into memory. So now what means lazy evaluation is that in PySpark we have something called transformations and actions. So, and PySpark only reacts and starts working once we hit an action. So we read in PySpark the data, then we have a transformation, which is the filtering in this case, and then we have, for instance, a count. That's an action where PySpark now says, okay, I have to deliver a result. And that's what means lazily. Because PySpark doesn't load all the data into memory, even if it does memory processing. The catalyst optimizer says, is there, roughly said, a more efficient way to do this activity? And for instance, in PySpark, in Paquet, we, for instance, have something which is called predicate pushdown. So what PySpark here most probably gonna do is, okay, it just loads the data with the column ID, because that's the only thing what I need to filter, and I don't need to know all the other columns, for instance, of this data set to perform a count. I just need column ID for doing my filtering, and then I can count. And I would come up to the same result as loading all the, let's say, 20 columns which the data has. And this is already a very big win to load less data into memory. And that's roughly said how this catalyst optimizer is working at the end. And that's one of the reasons why PySpark is just so efficient. The memory and the way it's optimizing in the background to process your data just very efficiently. And with that, I just want to shortly summarize what we learned today. So we learned that Spark supports different languages: Python, SQL, Scala, Java, and R. Seems like I forgot it here. So that's a statement I'm doing, but I feel like Spark is well supported by all cloud providers, and it's a quasi standard for big data in my point of view. We have a Pandas API if you want to start easily using Spark. Of course, I would highly recommend to check out the PySpark API, and it supports also streaming and batch processing, but also machine learning. So the Spark architecture we saw is built by a driver, multiple executors, and the cores determine your scalability and distribution of your dataset, which execute at the end the task. Well, and the high scalability and flexibility due to its parallelism is based on those partitions, on those breaking down the data into smaller pieces, which at the end are executing those tasks in the core. And the last thing what you just saw is that lazy evaluation, waiting until an action occurs, is one of the major improvements has been done in Spark with the SQL API on top, having this catalyst optimizer with the execution plan to optimize before the actual execution plan and transformations are performed. And with that, thanks a lot for listening. I hope you enjoyed this ramp up video of Spark. If you liked it, please like the video below, comment, and of course, subscribe my channel. And we see each other in the next video. Stay tuned.